Hello everyone, welcome to IFAS. Good evening everyone. Good evening. Good evening Royal Jutney. Okay, बहुत बढ़िया नाम है. Good evening Pratyusha, Nisha, Rutuja, Rohini. Okay, they are searching today. Chemical bonding lecture could not happen today. Nadeem sir is a little under the weather today. He is suffering from cold and a little fever, so he couldn't take a class today at 5 o'clock. But don't worry, he'll be back tomorrow. All right, there is a short break here for Nadeem sir's class, but he'll be back with his chemical bonding classes tomorrow. Okay, so don't worry about it at all. Okay. All right, so we are back here. Okay, I'm not feeling that. Yeah. All right. Okay, so I hope everyone is back here. Good evening everyone. Good evening. Good evening Nisha, Pratyusha, Rutuja, and we are back here with the second session of quantum chemistry. Unfortunately, I put a lecture 1 here. I'm so sorry for that. This is actually the second lecture. This is not lecture number 1. This is actually lecture number 2. And in this, what we are going to study in this lecture is free particles. Okay, what we are going to study is free particle systems. Okay, we are going to look at free particle systems. Okay, free particle systems are essentially systems which are on which no force acts on them. How my paid course will activate, sir, please help me. Shayoni, your paid course will be activated directly once you make a fee payment. I think you have to pay the fees and send a screenshot to our counselors. Once you do that, you have to download the IFAS app, and I think you have to share your login ID that you have generated. Once you share the login ID, the course will be activated on that particular login ID. So the next time after your course is activated, when you sign in, you will see a paid course there. Okay. Hello Gaganpreet. Good evening. Good evening. All right. So Shayani, if you have any doubts about it, about how the live course gets, how your paid course will get activated, don't worry. Just call our number. That number will be visible on the top comment. Okay. There is a yellow colored chemistry CSIR NET comment. All right. Just have a look at that comment. There are a few phone numbers mentioned in that comment. You can just call them, and you will get this. You'll get all the information about how the course gets activated. Okay, so don't worry. This is not something to worry about at all. We'll take care of it. Rutuja is saying that she can't see the PDFs on the app. Yes, Rutuja, for this particular series, the PDFs will be visible there. Just give me a few days. In the meanwhile, all the PDFs of Jazba 1.0 batch, which is the chemical bonding classes, all those PDFs you can now see on the app. Okay, all those PDFs are visible on the app. All right, so you can go and check. Chemical bonding lecture number 1 to 6 is there. I think lecture number 7 has not yet been uploaded, but that will also get uploaded soon. Okay, so all of those PDFs are the Jazba 1.0 batch PDFs are now available, and I'll also upload the group theory PDFs. Okay, we have done a group theory course. We have also done a the organic chemistry course where we studied GOC. Hitesh Maurya sir taught GOC, and even those PDFs will be made available on the app. All right, so just don't worry about those PDFs. I'm sure we'll get them. We'll ensure that they get uploaded and they are available for you there. Okay. All right. So let's go for today's class. Now, what we had discussed in the last class, let's quickly go over that. What we had discussed in the last class, let's quickly go over that. So we had discussed the difference between classical, or rather, to be more precise, rather than classical, particle nature and wave nature. Okay, we were discussing the difference between these two, particle nature and the wave nature. All right. And there were a few people who thought that light must be a particle. There were a few people who thought that light must be a wave. So particle nature, what all were they able to explain using the particle nature? They were able to explain reflection, they were able to explain refraction. They were also able to explain dispersion. Okay, they were also able to explain dispersion. Dispersion meaning splitting of light into various colors. Okay, splitting of light into various colors. They were able to explain using, they meaning Newton was able to explain. Whereas wave nature, phenomena like diffraction, then interference, then generation of electromagnetic waves by oscillating charges. All right, all these required us to assume that light must be wave like in nature. Okay, all of these phenomena required us to assume that light must be wave like in nature. All right, and who were the people who thought that light must be a particle? Who were the people who thought that light must be a particle? One was Newton. Okay, Newton's corpuscular theory of light, that was what gave us this. Whereas in wave nature, who started this? So at the time of, during the time of Newton, there was a mathematician called Descartes. Okay, in fact he's a natural philosophist, meaning so all of you have heard of the Cartesian coordinate system, and that Cartesian word comes from Descartes. Okay, so this Cartes finally converts to Cartesian. Okay, Cartesian coordinate system is x, y, z axis. All right, so that is the same Descartes that you can see here. All right, hello Mrunal, welcome to IFAS. René Descartes, yes, Descartes, René Descartes was his name, and he was a contemporary of Newton. In fact, if you go historically, these two people had a lot of conflicts. Okay, they were competitors in the field of science, in the field of you can say natural sciences or research, and they had a lot of sort of competition, healthy competition or maybe not so healthy. All right, and then you had Huygens. All right, Huygens was a big proponent of wave theory of light. In fact, Huygens theory was able to explain reflection, refraction as well. All right, so Huygens was one of the biggest competitors of this Newton's particular theory or the corpuscular theory that Newton had given, right? Then came Young. Okay, Young's double slit experiment is something that all of you have heard. Then came Maxwell. Okay, Maxwell gave the theory of electromagnetism, meaning why oscillating electric charges should produce electromagnetic waves, and this was proven by someone called Hertz. This was proven by someone called Hertz. Okay, all right, so all of you know this. Yes, correct, Mrunal. René Descartes was his name. All right, so these were all the scientists, or you can say physicists, who have contributed to this field. Okay, and finally after Newton, there was one more person who then came up and said that energy is quantized. Okay, Planck, what he suggested was E is equal to nh nu. Okay, where when Planck said this, Planck didn't realize that what he is actually doing is assuming that light must be a particle. What Planck was assuming was that the energy of light is quantized. Okay, energy of light has discrete energy levels. You can have 1 h nu, you can have 2 h nu, you cannot have 1.5 h nu. All right, good evening Sarfaran, good evening. So that's what Planck suggested. All right, and these were all the people who thought that it was particle nature. Okay, and after Planck is the biggest name that entered this. Okay, after Planck there was a big name who entered this sort of debate of whether light is a particle or a wave. And can someone tell me what this big name must be? I'll give you a hint. The hint is photoelectric effect. The hint is photoelectric effect. Okay, all right, Gaganpreet, I have checked today afternoon. I think in the Jazba course you will have in the Jazba course, all the PDFs are now visible. Okay, the PDF, when you click on the PDF button, because the PDF has a certain size, it takes some time for it to load in the beginning. But once you load it for the first time, just wait, click on PDF, wait for some time and let the PDF download. Once the PDF is downloaded, just wait for some time. All right. And once the PDF is opened for the first time, the second time you try to load that PDF, it will not take time. It will be very quick. All right. Yes, very good, Mrunal, Pratyusha, absolutely correct. Einstein was the other big name. Okay, so all the big names, all the big scientists that you have heard of, Newton, Einstein, both of them thought that light must be a particle. Okay, both of them thought that light must be a particle, whereas all these people thought that light is a wave, and no one believed them, most likely. I don't know, none of these are that famous. Maxwell is famous, Hertz is famous for the wave nature. Hertz is famous because he had some sort of work on radio. All right, radio waves was his area of expertise. Good evening, Hemant. Good evening. Good evening. So that's what these people contributed. Okay, so how did Einstein suggest that light must be a particle? Okay, because there was almost 250 years of research that pointed towards the fact, not even 250, I think almost 300 years of research that pointed to the fact that light must be a particle, light must be a wave. Okay, because Descartes was sometime around 1700 and Einstein was 1900, so that's 200 years at least, and Newton was 1640. All right, Huygens and Newton were also sort of contemporaries. So 250 years of research was suggesting that light must be waves, and 250 years ago one person thought that light is a particle. Okay, now comes Einstein in support of Newton, saying that yes, light must be a particle. Okay, yes, lustrous as the moon. Good evening. Good evening. So when Einstein said light is a particle, what basis did Einstein have for saying this? Okay, what was his logic? So before I tell you the logic, let me remind you that our English batch has started from 17th of October. All right, from this Monday, the CSIR NET complete English medium batch, the full English version batch has started, and you have a very good opportunity to learn from India's best educators in this particular app, and that too at a very, very affordable price. And what is that affordable price? Currently, IFAS is running a flat 70% discount for all CSIR NET courses, including the English batch. All right, and you will see that if you go to our website, if you go to the website of IFAS, and if you enter this promo code ITIHAS, ITIHAAS, okay, just make a note, there are two A's here. Okay, ITIHAAS. All right, if you enter this promo code, a flat 70% offer will be activated, and you will get the entire course in less than 10,000 rupees. Just go on our website www.ifasonline.com and just check it out. All right, don't even believe me, don't trust me, don't take my word for it. Just go to the website and check this out. You will see a flat 70% off on all these courses. Okay, so this sort of the English lecture series that we are running here in the Jazba 1.0 batch, you can say that it's a demo lecture series. It will tell you what kind of lectures, what depth we actually teach in our course. All right. Okay, now let me, before I tell you what Einstein actually did to sort of suggest that light must be a particle, let me tell you about the photoelectric effect. What is the photoelectric effect? The photoelectric effect is exactly this. There is a lamp, okay, that lamp shines some light onto an electrode surface. All right, now this electrode surface is a very special surface. Okay, this surface is a special surface. This is made up of some sort of a photoelectric material. This surface is some sort of a photoelectric material. Okay, or it is also sometimes called as the photocathode. It is also sometimes called as a photocathode. All right, and light shines on the photocathode. All right, what happens as a result is if you remember what cathodes are negatively charged. All right, And the photocathode, even if you look at this battery is connected to the negative charge of it. So there is an excess negative charge here. What happens as a result is, when light shines, if this light provides sufficient energy for an electron which is on the photocathode will start giving out electrons. It will start releasing electrons. All right, Lustrous as the Moon is asking, sir, group theory and GOC lectures 1.0 में add कर दीजिए. Yes, we will add GOC and group theory lectures also there. So don't worry, they will be added in the Jazba 1.0 folder. Okay, we are in the process, but if you go and check it right now, the chemical bonding lectures, the first 6 lectures have already been uploaded there. All right, and we will upload all the remaining lectures there as well. All right. Okay, so look at the photoelectric effect. Now look at the color of this light. Okay, in this diagram, the color of this light is also there, chosen on purpose. This light is UV. This light is UV. Okay, it is in the UV range, ultraviolet range. All right, and the reason for that is, if you remember what the ionization energies of atoms are. Okay, if you remember the ionization energies of the atoms, they are having energy similar to a UV photon. Okay, a UV light radiation, whatever energies those radiations have, okay, similar energies are ionization energies of atoms of these photoelectric materials. All right, and that's the reason why we are using UV radiations. All right, yes, thank you so much, Lustrous as the Moon. And I'll ask you to follow the example of Lustrous as the Moon. All right, so I'm sure that you are loving this lecture, and please show your love in the comments. Okay, in the comments as well as in the number of likes that you have for this lecture. There are 22 concurrent viewers and only 13 likes. That doesn't add up. Okay, that doesn't make sense. So please show your love in the comments also. Thank you so much, Rutuja. Nisha is saying, after updating app also, I can't see the PDFs in Jazba. In Jazba, you don't have to update the app. The first time the PDF loads, it takes some time because it's downloading the PDF from our servers. Once it downloads it, the second time you open it, it will open immediately. But the first time, it takes some time for the PDF to open up. All right. Yes, thank you so much, Pratyusha. Thank you so much. All right. So let's continue. Let's move ahead. UV light is shining on the photocathode, and now it is knocking off electrons. Okay, what it is doing is, it's knocking off electrons from the atom. As a result, what will happen is, these electrons, you can see here some small particles, you can see here, these are actually electrons. These are actually electrons which are actually moving in those directions. These are electrons. Some of the electrons have even reached here. Okay, these are electrons which have been knocked off atoms from here, and they are actually moving in that direction. All right, so this is what the photoelectric effect is, and as a result, there will be a current flowing in this circuit. Okay, as a result, there will be a current flowing in this circuit. Okay, is this clear? Lots of affection for the IFAS team. Thank you so much, Pratyusha. Thank you so much. You made my day by saying this. Good evening, Kanchan. Good evening. Good evening, Kanchan. Okay. All right. So this is what the photoelectric effect tells us. All right. This is what the photoelectric effect tells us. Okay. Now, what Einstein actually observed, or actually this experiment was not done by Einstein. Einstein was not an experimental physicist. Einstein was actually completely a theoretical physicist. So there were some observations made by someone else. Okay. And even Planck had actually made some of these observations. Arindam is asking, what is my full name? My full name is Rajiv Abhyankar. All right. Okay. So that's what Einstein was actually trying to explain, the observations of some experimental physicists, and the observations were for 3 different photocathodes. Okay, so this rubidium, potassium, and sodium, these are photoelectric materials. Okay, these are photoelectric materials. So if you make a photocathode made up of this or coated with these elements, rubidium, potassium, or sodium, what you find is that initially, so on this side there is kinetic energy of electrons, or you can say I, which is the photocurrent. Okay, what you are essentially plotting is the current. What you are plotting is the current. Okay, and what does this current tell you? That there are certain frequencies for each of these photoelectric materials below which there is no ejection of photoelectrons. Okay, below a certain frequency there is no ejection of photoelectrons, and above a certain frequency ejection of photoelectrons starts. All right. Yes, thank you so much, Pratyusha. Thank you so much. And it's really your motivation that keeps us going and keeps giving us this motivation to come up with such material for all of you. All right. Okay, great. So let's continue. So there is a certain frequency, and this frequency, these frequencies that you can see here, these are called as threshold frequencies. These are called as threshold frequencies. Okay, these frequencies are called as threshold frequencies. Now, what are these threshold frequencies? Okay, what do you think threshold means? Can someone tell me what threshold means? Can someone tell me what threshold means? Can someone tell me what threshold means? So threshold has a very interesting origin. The word threshold has a very interesting origin. All right, minimum needed, not necessarily. It actually ends up meaning that, but threshold means the boundary. Okay, threshold is a boundary. All right, so the story is, you can see that this word is a combination of thresh and hold. Okay, the word threshold is a combination of the word thresh and hold. Okay, thresh is essentially branches of a certain kind of a plant. Okay, and these branches, the dried branches are they are spread on the floors of houses, and this used to be done back in the 19th century. Okay, I am talking about 150 years earlier. Nowadays, in all our houses, we have floors which are made up of tiles, right? We have tiles on the floor, and you are from TIFR. Yes, I used to work in TIFR a long time back, 10 years earlier. All right, I used to work in TIFR. All right, so thresh is actually the branch of a plant. Okay, and it's soft in nature. So what happened was, 150 years earlier, in some of the houses, usually they didn't have a smooth floor. Nowadays we are using tiles, so so floors are completely smooth, right? But when you didn't have smooth floors, walking in your house will become a little, problematic, uncomfortable. So what they used to do was, they used to have branches of this thresh, and they used to spread these branches on the floor. Okay, but because at that time you won't have a lot of multi-storied houses. Also, most houses are on the ground floor. It's a hut. Sometimes it's just a small hut, and you have spread thresh on the ground. It's a branch. So if you have a lot of wind, these branches are going to go away. These branches are going to get carried with the wind. Okay, so in such a case, what do you do? In order to hold the thresh inside the hut, what you used to do was, you have a raised platform right at the door. Okay, which we call the boundary. Okay, in Hindi we call it chaukhut, or in Marathi we call it umbra. Okay, so that's sort of the boundary of the room or your house, right where the door frame is there. Okay, so the base of the door frame is slightly elevated. So that what happens is, if thresh tries to go away with the wind, it will be held inside the room. So something that is used to hold the thresh inside is called as the threshold. Something that is used to hold the thresh, that is called as the threshold. Okay, and the threshold is the boundary. Threshold is sort of the limit, you can say, of the house or of the room or of the floor. Okay, good evening, honey. Good evening, Deepak. It's okay. You're not that late. We have just started. You're not that late. We are just started. So Arindam, how do you know that I am from TIFR? Arindam, how do you know that I am from TIFR? I don't think I have met you before earlier. How did you know that I used to work in TIFR? Deepak, I think you are attending this class for the first time. May I know where you are from? Where are people in this class from? So I know that Pratyusha is from, I think, Andhra Pradesh, Andhra, if I'm not wrong. Oh, you checked my ResearchGate profile. Okay, fine, fine. So that was a long time back. That was a long time back. All the entries there are from at least 10 to 12 years earlier. Yes. So Arindam, where are you from? Deepak, where are you from? Honey, I know, is from Gujarat, if I'm not wrong. Correct me if I'm wrong. So where are you guys from? Where are you from? Okay, anyway, so let's continue with this. So the photoelectric effect, it has a boundary, it has a limiting frequency above which you will start seeing photocurrent. Okay, above which you will start seeing photocurrent. Ritu is from Haryana. Welcome, Ritu. Yes, Nisha is also from Kerala. Nisha also I remember. Arindam is from West Bengal. All right. Which is the promo code? Oh, okay. You want the promo code? The promo code is ITIHAS. ITIHAAS. Okay, so that's the promo code. ITIHAS. ITIHAS in Hindi means history. ITIHAS means history. Okay, so Musharraf is from Kashmir. Hello, Musharraf. Welcome to IFAS. Anjali, GATE PYQs. Yes, absolutely. As the GATE exam approaches, I am sure that all of you are now worried about the GATE previous year questions. So in this lecture series, we are going to solve a lot of GATE previous year questions. All right, so don't worry. Yes, absolutely. Absolutely. So Arindam, welcome. Disha, Ritu, welcome. Nisha is always welcome. Nisha has been with us for a long time. So Musharraf is from Kashmir. Welcome, Musharraf. So I just have one request to all of you. So if you're liking these lectures, please share the link of this video. All right, so that other people also come to know about this wonderful series that's going to teach you the very basics of quantum chemistry. All right, let's continue. So this is photoelectric effect. But now our main point for studying the photoelectric effect is to understand why Einstein considered that light must be a particle. Okay, to understand why Einstein considered that light must be a particle. Okay, so that's what we are trying to understand. Okay, now this doesn't really tell us that light is a particle. What it tells us is that the energy of the photon is frequency dependent. Okay, what it simply tells us is that the energy of a photon is frequency dependent. Okay, but there was another observation that was made in the same experiment. What was the other observation? If you plot the photocurrent, with frequency, of course you are going to see something like this. Okay, initially no photocurrent, but above the threshold frequency you will start seeing a photocurrent. Above the threshold frequency you start seeing a photocurrent. But even going further, what you will realize is that if you increase the intensity, all right, if you increase the intensity, so this is I3, this is I2, this is I1, and in this direction we are increasing the intensity. Okay, and as intensity increases, what you can see is that the amount of photocurrent is also increasing. As intensity increases, the amount of photocurrent also increases. Now, what do you mean by intensity? Intensity is energy per area per second. Energy per area per time. That is intensity. Okay, so let's go back to our photoelectric effect experiment. Okay, there is some energy which is incident on the photocathode from this lamp. Okay, and that energy is being absorbed by electrons. And if an electron gets sufficient energy to be released from the atom, the electron will be released and you will start seeing a photocurrent. Okay, so that's the principle here. Okay, now the point is, if the intensity is increased, you should get more photocurrent because more energy is being absorbed. Okay, more energy is being absorbed. So which is why you should get a higher amount of photocurrent. But there is something that you should notice, is that this threshold frequency, okay, this threshold frequency, the interesting point here is not that the intensity increases. That is something that's expected. Okay, increase of the intensity is something that is expected. But what was not expected here was that the threshold frequency is independent of intensity. The threshold frequency is independent of intensity. Okay, so if you use a higher intensity light, what we expect is even at a lower frequency you should start seeing photo emission. Okay, because it's a wave nature. Suppose light is wave in nature, what will happen is, because the intensity is higher, every electron now can absorb more energy from a wave and it will start getting ejected. So there should be no concept of threshold frequency there. But what happens here is that the threshold frequency is independent of intensity, but above and beyond the threshold frequency you will see current which is intensity dependent. You will see current which is intensity dependent. And this was the point that tells us that light is not a wave, it's a particle. Because when the electron absorbs energy, it's not absorbing energy in the form of a wave. It's absorbing energy in the form of either one photon or two photons or three photons and so on and so forth. Normally, whenever such photoelectric emission takes place, the intensities that we use are so low that at a time an electron only has time to absorb one photon. So either it gets all the ionization energy from that photon or it doesn't. If it doesn't, the frequency of the photon must be lower. If it does, then the frequency of the photon must be higher. All right, and which means if we are talking about photons, or sometimes they write this as energy packets, or quanta, energy packets or quanta or photons, energy packets or quanta or photons. All right, and what this tells us, the intensity independence of the threshold frequency tells us that energy is being absorbed not in a continuous format, not as a wave, but in the form of packets of energy, and which means that these packets are essentially particles of light. Okay, good evening Kauleshwar, good evening Pooja, welcome, good evening all of you. So that is the main point of the photoelectric effect experiment. Okay, that is the main point of the photoelectric effect experiment. Is this clear to all of you? Any doubts here? Okay, so what this photoelectric effect finally tells us is that whatever kinetic energy, or let's say not the kinetic energy, let's start with whatever is the energy of the incident photon, that is h nu 0 plus 1/2 mv square. This assumes that energy of one packet or one photon E is equal to h nu. This is what is called as the quantization principle. This is what is called as the quantization principle, which we have seen in the last session also. And this was something that was proposed by Planck, and this was something that Einstein utilized to actually come up with an explanation for the photoelectric effect. All right, have you understood all of this? Thank you so much, Suresh, Rutuja, Arindam. Yes, h nu 0 is a work function. I'll explain what each of these are. Okay, so this is the quantization principle. Now this h nu 0 is also called as work function phi, or sometimes written as w. And what is this half mv square? Half mv square is the kinetic energy of an electron. Half mv square is the kinetic energy of an electron. This is the kinetic energy of an electron. Okay, got it? Got it? Now what is the work function? Work function is essentially, so phi or W, this is equal to h nu 0, where this nu 0 is the threshold frequency. This is the threshold frequency. Okay, this is called as the threshold frequency. Is this clear to all of you? Is this clear to all of you? All right, is this clear to all of you? Any doubts here? I'm sure that there are no doubts. I'm sure that you have all understood this. And the interesting fact about this is, if you have understood this, even you could have won the Nobel Prize. Okay, even if you had understood this, even you could have won the Nobel Prize, because the 1922 Nobel Prize, 1922 Nobel Prize went to Einstein, and we were all surprised that this Nobel Prize Einstein didn't win for his theory of relativity. Okay, it is said that back in 1922 no one really understood the theory of relativity. Okay, but they were now so ashamed, the Nobel Prize committee was so ashamed that they have still not given Einstein a Nobel Prize. All right, and the community overall was saying that relativity is a very fundamental theory. They were so ashamed that they had to give Einstein a Nobel Prize, but they couldn't give Einstein a Nobel Prize for a theory which didn't have real life applications. Okay, the real life applications came much later. Okay, the atomic bomb was invented much later. So back then they wanted to honor Einstein by giving the Nobel Prize. So what they decided was, what the hell, let's give Einstein a Nobel Prize for the photoelectric effect. So Einstein actually won the Nobel Prize not for the theory of relativity, but for photoelectric effect. But for the photoelectric effect. All right, and if you have understood this, back in 1922 even you could have gotten the Nobel Prize. That's the most interesting part of all of this. All right, so we are all now Nobel Prize winners because we have understood something that got Einstein, even the great Einstein, got the Nobel Prize for something as seemingly simple as this. Of course, this is not that simple to understand. Okay, back then there was no Google, there was no internet, so Einstein had to search for so many research papers to even get data for this. All right, so it was not an easy task for Einstein either. Okay, so this is what is the photoelectric effect. Okay, now before we actually continue, let's solve a question on the photoelectric effect. Let's solve a question on the photoelectric effect. Suppose that what can we do for this? Suppose the kinetic energy, for a particular metal, okay, for a particular metal, the frequency when it was 10 raised to 14 hertz, when the frequency was 10 raised to 14 hertz, okay, then the kinetic energy was 5 electron volts. Okay, then the kinetic energy was 5 electron volts. When this frequency is changed to 10 raised to 15 hertz, then what would the kinetic energy be? Okay, this is the question that we have to figure out. Okay, this is the question that we have to solve. Okay, now let's try solving this question. Okay, so at one incident frequency, the kinetic energy is 5 electron volts. At another incident frequency, what should the kinetic energy be equal to? Okay, this is what we have to try to figure out. This is what we have to try to figure out. And remember, equation is kinetic energy, or half mv square. Okay, if you remember the equation that we wrote last time, h nu is equal to h nu 0 plus 1/2 mv square, meaning this is the kinetic energy. So what is the kinetic energy equal to? That is h nu minus h nu 0. Okay, this is the equation that we have to finally end up using. This is the equation that we have to use, or you can even take h common here. You can even take h common here and just write nu minus nu 0. Just write nu minus nu 0 in this case. All right. Now, how do we solve something like this? How do we solve this particular equation? Okay, how do we solve this particular equation? That's what we have to figure out. Okay, that's what we have to figure out. Can someone suggest how we solve this? Can someone try to tell me how we can solve this? We want to calculate the kinetic energy when nu2 is 10 raised to 15 hertz. When nu2 is 10 raised to 15 hertz, what is the kinetic energy? That's what we want to calculate. Okay, can someone suggest how to do this? Can someone suggest how we can do this? Any ideas? Any ideas? Now, the first thing that you should remember about this is, remember when we talked about the work function. The work function is a characteristic of the material. Okay, work function phi. So, nu 0 or phi is a characteristic nu 0 or phi is a characteristic of what? Of the photoelectric material used. It is a characteristic of the photoelectric material used. Okay, now in both of these cases, you will notice that the same metal is being used. In both of these cases, the same metal is being used, meaning this nu 0, the value of nu 0 should be constant. Do you understand this? What this means is that the value of nu 0 must be constant. Is this clear to all of you? The value of nu 0 must be constant. Is this clear to all of you? Okay, the value of nu 0 must be constant. Is this clear? Okay, so that's one thing that we already know. That's one thing that we already know. Okay, and then how do we calculate nu 0? How can we calculate nu 0? In order to calculate nu 0, what we will have to do is h nu 0 will be equal to h nu minus kinetic energy. And what is h nu? Nu 1 is given and kinetic energy is also given, but that's in electron volt, so we'll have to figure out. So h into nu, h is 6.6 into 10 raised to minus 34, and nu 0, what is nu 0 equal to? Nu 0, or nu 1, that is equal to 10 raised to 14 hertz, and this minus the kinetic energy, the kinetic energy given is 5 electron volts. So this will be 5 into 1.6 into 10 raised to minus 19. Okay, this will be 5 into 1.6 into 10 raised to minus 19, and this answer will finally be in joules. Okay, this answer will finally be in joules. Okay, so how much is this? Actually, this won't even work out. I'll have to change the numbers here maybe slightly. Instead of 5, let's do 0.5. Okay, instead of 5, I'll just write 0.5 here. Okay, instead of 5, I'll write 0.5 here, because otherwise our answer won't work out. So 0.5 electron volts. Okay, 0.5 electron volts. So now what would the answer be? So this comes out to be 6.6 into 10 raised to minus 20 minus 0.5 into 1.6, that comes out to be 0.8, so that's 8 into 10 raised to minus 20 again. Or even this won't work out, even this won't work out. Hang on. Okay, so fine, let me change these numbers also. Instead of 10 raised to 14, I will just write 5 into 10 raised to 14. Let me just write 5 into 10 raised to 14 hertz here. Okay, just so that our answer works out. I just want to demonstrate the method by which we want to solve this. Okay, so 5 into 10 raised to 14. Okay, and this will become 6. 6.6 into 5 into 10 raised to 14. Okay, that's what we'll use here. So what we have done is nu1 equal to 5 into 10 raised to 14 hertz. That gives kinetic energy as 0.5 electron volts. So nu2, if that is 10 raised to 15 hertz, we want to calculate kinetic energy is how much. Okay, that's the question that we are essentially trying to solve. Okay, so h nu 0 becomes this. So 6.6 into 5 will be 33, and you will get a 33 here. You will get a 33 here. 33 minus 8 gives 25. So 2.5 into 10 raised to minus 19, and this answer is in joules. Okay, this answer will be in joules. Is this clear to all of you? Is this clear to all of you? What we have done, we have simply calculated the work function right now. What we have done is we have calculated the work function, and now based on this work function, how do we calculate kinetic energy? So therefore, what is kinetic energy equal to? Kinetic energy is h nu 2 this time minus h nu 0. Now h nu 2 is 6.6 into 10 raised to minus 34 into 10 raised to 15 minus 2.5 into 10 raised to 19 minus 19. 2.5 into 10 raised to minus 19. Got it? And if you solve this, this is now okay, again right, 6.6 this becomes 10 raised to minus 19. So 6.6 minus 2.5, that comes out to be 4.1 into 10 raised to minus 19 joules, and that's your final answer. And that's your final answer. Is this clear to all of you? Is this clear to all of you? All right, so what we did was, because to calculate kinetic energy we need h nu 2. Nu 2 is given, but what we require is h nu 0. What we required was h nu 0. So what we did was we calculated h nu 0 first using the first part of the information given. This gives us h nu 0. All right, and then you use this part to calculate kinetic energy. All right, so step by step, write the first equation or write the final equation. Kinetic energy is h nu 2 minus h nu 0. You realize that nu 2 is given, but h nu 0 we don't know. So calculate h nu 0. So we calculated h nu 0 from this, and then we reach the final answer. A similar question was asked in the last GATE exam. Okay, or sorry, maybe CSIR NET exam or GATE exam. I don't remember very well. But in this February, the NET and GATE exams both happened. And in one of those exams, exactly a similar question was asked. Okay, exactly a similar question was asked there. Okay, is this clear? Is this clear now to all of you? Is this clear to all of you now? Any doubts here? Any doubts? What is power? 10 raised to minus 19. 4.1 into 10 raised to minus 19. Okay. Now, I am sure that no one is asking this, but I am also sure that all of you have not understood that 10 raised to minus 19 and where this came from. So let's try figuring that out also. Now, before we go ahead, if you want more such questions, okay, one of the best books available in the market for physical chemistry is our Physical Chemistry Concept Check. This book has more than 3,000 practice questions. All right, this book has more than 3,000 practice questions. Okay, concept dekho, calculation nahi, no. You should actually have a look at both the concept as well as calculations, because I know that a lot of students actually struggle with the calculation. So in case you have any problems with the calculation, ask me. Like for example, yes, Nisha is asking that electron volt to joules conversion. All right, so I'll explain that conversion also. But before that, let me tell you that questions of the same difficulty level, say questions of a better quality even, are present in this Physical Chemistry Concept Check book. And I believe that because I myself have worked on this book, I myself have written this book, and I know this book to be one of the best physical chemistry books for competitive exams out there. Okay, so if you want a one-stop solution for all your physical chemistry practice requirements for CSIR NET, GATE, BARC, TIFR exams, SET exams, Public Service Commission exams, even the UPSC Geoscientist exam, or of Diwali, we are offering a specific sale for this book, and this book normally costs 795 rupees, but we are actually putting this at a cost of 500 rupees. So I think we are not making anything from it now. I know that we are not earning any profit from it. So like my fees for this book are zero now. I'm sure that I'm not going to get any fees for this. But we would like all the students to get a taste of how good physical chemistry questions actually look like, and which is why we are making it available at an extremely affordable price. So make sure that you go ahead, go to our website www.ifasonline.com, and make sure that there is a sample PDF of this book available there. Just go through the sample PDF so that you get a good idea of what all you can expect in this book. All right. Okay. So now let's look at the electron volt to joule conversion. Now what we know is 1 electron volt is 1.6 into 10 raised to minus 19 joules. 1.6 into 10 raised to minus 19 joules is 1 electron volt. Now what we have to actually figure out is the kinetic energy was 4.1 into 10 raised to minus 19, but this was in joules. Suppose I want to convert it to electron volts. Okay, suppose I want to convert it to electron volts. How do I convert it to electron volts? So what you should do is try to get rid of the joules. Try to get rid of the joules. Now how do I get rid of the joules? I want the answer in electron volts, so I'll write electron volts at the top. I don't want the joules, so I'll write joules here. Okay, and now what I'll do is, there is some quantity in electron volts which is equal to some quantity in joules. I'll write those numbers here. So now I know that 1 electron volt is 1.6 into 10 raised to minus 19 joules. And if you solve this way, you'll immediately realize that the units that you don't want, they get cancelled off. The unit that you want survives, and you'll directly get the answer. So you don't even have to think about whether you have to multiply these two numbers, divide these two numbers, is it this upon that or that upon this? You don't even have to think. Let the units tell you what to do. If you have joules here, try to get joules cancelled off. So write joules there. And 1.6 into 10 raised to minus 19 joules was 1 electron volt. So you automatically end up with the answer. You will realize that the 10 raised to minus 19 will also get cancelled out. And your answer is 4.1 upon 1.6, which is slightly over 2.5, which will be close to, I think, how much will this be now? This is close to 2.56, I think, electron volts. Okay, 2.56 electron volts. It's close to that. It's not exactly that. I'm sure you can check it out. You can just use a calculator and check it out. It's 2.56 electron volts. Okay, it's 2.56 electron volts. Is this clear to all of you? Is this clear to all of you? How to convert electron volts to joules and joules to electron volts? Okay, now let's come to our main point of this particular class, which is free particles. Okay, the main point of this class is free particles. The main point of this class is free particles. Okay, now what are free particles? What are free particles? New idea, I always get confused or thinking multiply or divide. Yes, absolutely. You don't even have to worry about whether to divide or whether to multiply. Let the units guide you. Okay, just remember one thing, in physical chemistry questions, all the hints are there in the question itself. All the hints are there in the question itself. You don't have to invent something new to solve a question. It's right there in front of you. Okay, now what are free particles? What are free particles? Free particles are particles where the potential is zero. Okay, free particles are particles where the potential is zero. Okay, now for this, there are two things that we have to understand. One is what is called as the wave function. One is what is called as the wave function. and the other is what is called as the energy. Okay, what is the wave function for a free particle if v equal to 0, or to be more specific, you can write Vx equal to 0. And what is the wave function and what is the energy of such particles? Now, first of all, for understanding this, we have to understand what the wave function is. Okay, to be able to understand this, we have to understand what the wave function is. Okay, all right. Okay, so now if any of you have not liked this session or shared the link of this session with your friends, or put it on your WhatsApp status, and more importantly, if you like this session, if you like the explanation that we are having, please share this session. Okay, just post the link on your WhatsApp status or post the link on your social media, just WhatsApp groups of your friends, so that even they come to know how quantum chemistry should really be learnt. Okay, quantum chemistry is not integration and formulas and weird looking equations. Quantum chemistry is full of concepts. And what are those concepts? Even if you understand the concepts without understanding even a hint of numericals, I think you will still be able to solve at least 3 to 4 questions out of the 10 questions of quantum chemistry that you get. All right. Yes. Thank you so much, Hani. Thank you, Mahir. Thank you so much. Okay. So what is the wave function? First of all, let's understand what is the wave function. What is a wave function? What is a wave function? Let's first understand this. What is a wave function? Okay, now wave function is something that gives you an idea about the uncertainty. Okay, wave function is something that gives you an idea about the uncertainty. Okay, so wave function actually tells you if the wave function is psi, then psi square is equal to the probability, or more precisely, probability density. Okay, so higher the value of the wave function, higher is the value of the wave function, or higher is the value of the square of the wave function, higher is the value of psi square, higher is the probability that a particle exists in the system. Okay, that is what it means. So for example, if you plot a wave function like this, if you plot psi square like this, okay, or actually let's not draw it like this, let's draw it like let's draw it like this. Okay, let's draw a wave function like this. Where is the probability of the particle existing the highest? Suppose I name these points as A, B, C, D, E, F and G. Okay, so what we have plotted is psi square against the x coordinate. So can you tell me, if you understand that the wave function means probability, if the wave function has something to do with probability, out of these points A, B, C, D, E, F, G, where do you think is the probability the highest? Where do you think is the probability the highest? Very good, Mahir, very good. This is called as the Max Born interpretation. This is called as the Born interpretation. Not Born representation, but it's called as the Born interpretation. Okay, this is the interpretation that Max Born gave for what wave function is. This is called as the Born interpretation. Absolutely correct, Mahir. Very good. Very good. This is called as the Born interpretation. This is called as the Born interpretation. Okay. So now, can someone tell me A, B, C, D, E, F, G, of these points, where is the probability the highest? Where is the probability the highest? Very good, Mahir. Probability is the highest at D. Probability is the highest at D. So at D, you will find the highest probability. At D, you will find the highest probability of a particle existing. So if this is your system, if this is your quantum mechanical system, and if you put a particle there, the particle will spend the most amount of time near the point D. The particle will spend most amount of its time near the point D. Okay, that is what the wave function tells you. That is what the wave function tells you. All right, and in fact, this probability is also related to a quantity called as the uncertainty in position. Okay, this is also uncertainty in position. So this is something related to the uncertainty principle. Uncertainty principle. What does the uncertainty principle tell you? What does the uncertainty principle tell you? Can someone tell me what does the uncertainty principle tell you? Or can you at least tell me what Heisenberg, which was the scientist who actually gave this principle? Can someone tell me which scientist gave this principle? What was the name of the physicist who gave us this principle? Can someone tell me this? What was the name of the physicist who gave us this principle? Can someone tell me what was the name of the physicist who gave this principle? I'm sure all of you have heard of this. I am sure that all of you have heard his name. In fact, I almost said the name right now. Yes, Shaleen is absolutely correct. Ritu, absolutely correct. Absolutely correct. Very good, Shaleen. Very good, Ritu. Pratyusha, Mahir, Shanu. Absolutely correct. Heisenberg. This principle was given by Heisenberg. Okay, this principle was given by Heisenberg. And what does Heisenberg tell us? What does Heisenberg tell us? That delta x into delta p is equal to h upon 4 pi. What is delta x? What is delta x? Delta x is position uncertainty. Delta x is the position uncertainty. Okay, whereas delta p is the momentum uncertainty. Delta p is the momentum uncertainty. Okay, one is the position uncertainty, one is the momentum uncertainty. Okay, some uncertainty present in position and momentum. Very good, very good. And this was the uncertainty principle given by Heisenberg, and this is again directly related to another principle that we have seen, which is de Broglie equation. De Broglie equation. Okay, what does de Broglie equation tell us? What does the de Broglie equation tell us? Do you remember? This says that lambda is equal to h upon p. Lambda is equal to h upon p. Okay, lambda is equal to h upon p. Now, what does lambda mean? Lambda is the wavelength, whereas p is the momentum. P is the momentum. Okay, now why are we suddenly talking about Heisenberg uncertainty principle and de Broglie equation? Because the most important point is we started our discussion by trying to think about whether light will be a particle, light will be a wave, and we didn't know. Newton said particle, everyone else said wave, and suddenly Einstein comes and says particle. Okay, that's what we learned in the photoelectric effect. Okay, now what is the truth? Because some phenomena are only explained by the wave nature of light, like for example diffraction, interference. They are only explained by using the wave nature of light. Okay, they are only explained by using the wave nature of light. Just a minute everyone, just a minute everyone. All right. So yes, now the point of de Broglie's equation was that every material particle, like we are talking about particles have momentum, right? All particles have momentum, mass into velocity, that is called as momentum. But what de Broglie equation tells us, that anything that has momentum also has wavelength. And you will immediately notice the word wave written here, and you will immediately notice the word wave written here. Okay, you will immediately notice the word wave written here. Okay, and now we are sort of reaching where we wanted to reach. Is light a particle? Is light a wave? What do you think? What do you think? Is light a particle or is it a wave? Is light a particle or is it a wave? Mahir is saying any moving body should possess some waves with it called matter waves. Okay, okay. But will it be, so suppose I am talking about an electron. Is an electron a particle or is it a wave? An electron has momentum. We have all heard of the angular momentum of electrons or the orbital angular momentum of electrons. We have also heard of wavelength associated with something that has momentum. So if an electron has momentum, it also means that it has some sort of wavelength associated with it. It has some sort of wavelength associated with it. Absolutely correct. Pratyusha, Nisha, Ritu. The de Broglie equation, what it tells us is that there is wave particle duality. There is wave particle duality. Okay, and that's the most important point here. Okay, that is the most important point here. That 400 years worth of debate, okay, almost not 400, 300 years of debate on whether light is a particle or a wave. All right, so all of you know that if you are debating about something, one person says this, the other person says that, one person has evidence of this, the other person has evidence of that. Okay, like for example, you are debating whether gulab jamuns are better or whether jalebi is better, sweets are better, rasgullas are better, let's say. So one is saying gulab jamuns are better. Okay, gulab jamuns, both are round objects, right? Rasgullas are also round, gulab jamuns are also round. Okay, now are gulab jamuns better or rasgullas better? What do you think? What do you think? So all the students who are sitting here, let's take a vote. Okay, what do you think? Are gulab jamuns better or rasgullas are better? Honey likes both. Honey likes both. Okay, fine, right? Yes, honey must be. Okay, Nisha also likes both. Okay, fine. Okay, fine. No one likes one more than the other. I like rasgullas more than gulab jamuns. I like rasgullas more than gulab jamuns. Okay, is there someone who likes gulab jamun more than rasgulla? Suppose you have to choose only one of them. Okay, so everyone is saying both. Don't worry, I'm not going to give you either of them. Okay, I neither have a rasgulla right now and nor have gulab jamuns. Okay, so honey loves all sweets. I can understand honey, absolutely. Nidhi also loves all sweets, but of course you have some preference, right? Okay, Ritu likes gulab jamun more. Nidhi likes rasgulla more. Okay. All right. Some are saying they like gulab jamun, and okay, gulab jamun and this is different. Okay, let's try another question then. What do you like more, tea or coffee? What do you like more, tea or coffee? I'm sure that there is an answer here. Every person likes either tea or coffee. No one likes both, typically. What do you like, tea or coffee? Gulab jamun and rasgulla is a controversial issue. But tea, okay, see, honey likes not just tea but green tea. Nisha likes coffee more. Okay, great. Nidhi also likes tea. All right. Mahir likes tea. Okay. Nidhi also likes tea. Okay. I like coffee, for example. I like coffee more. Pratyusha is same pinch with Nisha. Okay, Nisha also likes coffee. All right. Shanu also likes coffee. Great. Okay. So we have both tea lovers and coffee lovers. And is there a reason why? So which one of these should be best? Should it be tea or should it be coffee? Which one is better, tea or coffee? Which one is better, tea or coffee? So I'm sure that now everyone is thinking, better, I like tea more, so tea must be better. Someone is saying, I like coffee more, so coffee must be better. All right? Yes, I like coffee. Nisha is saying, what do I like? I like coffee, but I also like tea. Okay? So whichever is available, I'll go for it. Whichever is available, I'll go for it. Okay, like for example, if I am going outside, if there is a tea stall in front of me, I go and have tea. Okay, if I go to Barista or Cafe Coffee Day or whatever your coffee shops are, then I'll have coffee there. I'll not have tea there. But there are some places where I will also have green tea, just like honey. I'll also have green tea with some honey, of course. All right, green tea is not very tasty, so I'll add some honey to it and I'll have green tea there. Okay, just like honey. All right. Okay, so now there is a debate here. Okay, and now if someone starts debating, there has to be some person who comes and says, okay, chalo, it's not working out. This is better or that is better, we don't know. Let's compromise. Okay, let's compromise. Both of them are equally good. It depends upon what you're used to. Okay, it depends upon what you're used to. If you have had tea your entire life, you'll probably like tea. If you have had coffee your entire life, you'll probably like coffee. If you're a person like me, all right, who doesn't care which one is better, I like both, then I'll have both. Okay, Louis de Broglie is exactly like me. Okay, Louis de Broglie was exactly like me. And he, in fact, liked both theories, wave theory as well as particle theory. So what he said was, light is simultaneously a wave as well as a particle. Okay, light is simultaneously a wave as well as a particle. Okay, and not just light, material particles are simultaneously waves and particles. Okay, material objects are simultaneously waves and particles. Now, what does this mean? I am sure that all of you are now wondering. Suppose I say that electron is a wave and a particle simultaneously. Electron is a wave and a particle simultaneously. What does it mean? I am sure that all of you start thinking that if this is an electron, it goes like this. Right? So if an electron is a wave, it means that the electron goes like this. Is this correct? If an electron is a wave, electron must go like this. Is it correct? Is that right? In its PhD thesis and win Nobel Prize. Yes, yes. I think this was who? Louis de Broglie. You don't know the half of it. You don't know the half of it. Look at the age at which he got his PhD and look at what the background of Louis de Broglie is. That's more interesting. Louis de Broglie was not just a scientist or a physicist. He in fact got this hypothesis at the age of 23. He completed his PhD at the age of 23, and if I remember correctly, at the age of 23 I was struggling to finish my MSc. All right, at the age of 23 I was struggling to finish my MSc. Louis de Broglie got his PhD thesis at the age of 23, and not just that, he was not just any other student, he was actually a prince of a country. Okay, Louis de Broglie was actually a prince of a country. Okay, so that actually tells you what a person should do when they have a lot of resources at their hand. Okay, that actually tells you that so if you have a lot of resources, yes, 1924 I think, correct. So I think he was 23 years of age. Just correct me if I'm wrong. I think he was just 23 years of age, Louis de Broglie. He was not very old when he completed his PhD thesis. That got him a Nobel Prize. Maybe he got the Nobel Prize at a much later age, but he completed his PhD at a much earlier age. Okay, if you like this information, show some love again in the comment section. Okay, Honey is 19, turning in 20 in 2 months, and I am in MSc final year. So Honey has 3 more years to earn the Nobel Prize. Honey has just 3 more years. In 3 years, Honey is going to finish his PhD thesis and he is going to earn the Nobel Prize. Okay, excellent. So if I've inspired you to do that, yeah, my job here is done. Okay, Chichore friends are saying tea with samosa. Okay, great, tea with samosa. Okay, fine. Okay, so now what we were discussing was electron is a wave as well as a particle. Does it mean this? Absolutely not. This is not what it means. This is not what it means. What it actually means is, if you have an electron here, and if you send the electron along this path, okay, and you have a screen here, okay, if you send an electron in that direction, okay, if you simply send an electron in that direction, okay, where do you think the electron will end up at this place? correct? The electron will end up at this place. That's our expectation. All right, the electron will end up at this place. That is our expectation. But in actuality, what happens is sometimes, so suppose you send 100 electrons. If you send 100 electrons, all electrons won't be visible here. There will be some electrons that you observe here, more electrons right at the center, and some electrons here. Okay, so you will find maximum number of electrons right here, but there will be some electrons that will end up there also. Some electrons will not follow the straight line path. Some electrons will not follow the straight line path. And if you actually construct the probability curve, that probability curve comes like this. If you make a probability curve, that probability curve looks like this. And this probability curve, okay, the width of this probability curve, is delta x. The width of this probability curve is delta x, and that is the uncertainty in the position of the electron. So I sent the electron in this direction. I was certain that the electron must be here, but my observations tell me that the electrons end up sometimes there, sometimes here, and which is why this becomes the uncertainty in electrons. This becomes the uncertainty in the position of an electron. Okay, is this clear? So this becomes the uncertainty in the position of an electron, and this uncertainty arises because there is a wavelength associated with an electron. And what wavelength means is the uncertainty itself. What the wavelength means is the uncertainty itself. Okay, so this is why I actually wrote both of these principles on the same slide, because the uncertainty principle and the de Broglie equation are almost one and the same. They are actually talking about one and the same thing, which is wave particle duality of matter, of particles. And this wave particle duality is also seen in free particles. This is also seen in free particles, wherein the wave function is written as e raised to plus or minus I kx, e raised to plus or minus I kx, and this energy comes out to be k square h cross square upon 2m. Energy is k square h cross square upon 2m. So the wave function is represented like this. Okay, the wave function is represented like this. Okay, so a free particle, just like an electron, has a position uncertainty, and the function that describes the position uncertainty, or the the wavelength of a particle, the function that describes the position uncertainty or the wavelength of the particle, that function is what is called as the wave function. That function is what is called as the wave function. Here this k is actually equal to 2 pi upon lambda, and we all know what this lambda must be meaning. What would this lambda stand for? This is the de Broglie wavelength. This is the de Broglie wavelength. This is the de Broglie wavelength. Is this clear to all of you? Is this clear to all of you? Okay, so free particles, particles which don't have any force acting on them, okay, wherein the potential energy of the particle is 0. For them, the total energy comes out to be that, and the wave function comes out to be this, where k is 2 pi upon lambda. So all of you who remember your physics, 2 pi upon lambda is also called as something called as the propagation constant, and that is exactly a constant which is used for a wave-like nature. So we are talking about a particle and we are writing its wave function, and that is because there is a wave particle duality. That is because this is a wave particle duality. All right, is this clear? Now the most interesting thing about this energy that we see, for a free particle, energy is equal to k square h cross square upon 2m. K square h cross square upon 2m, and k is equal to 2 pi by lambda can have any value, okay? The value of k can be anything. If I change the wavelength, the value of k will change. If I increase the wavelength, k will decrease. If I decrease the wavelength, k will increase. They are inversely proportional to each other, which means 2 pi upon lambda can have any value. 2 pi upon lambda can take any value. And as a result of this, because 2 pi upon lambda can take any value, energy is a continuum. Energy is a continuum for a free particle. For a free particle, energy is a continuum. What this means is for a free particle, the energy level diagram, if we draw the energy level diagram for a free particle, what we are going to see is this is energy, and this is actually a continuum. Even this energy is allowed, even this energy is allowed, even that is allowed, even that is allowed, even that is allowed. But on top of that, any energy in between, they are also allowed. Any energy in between these, they are also allowed, and so on. So there is a continuous energy spectrum here available, and that is available only for free particles. There is a continuous energy spectrum available, and that is only for free particles. Okay, in energy equation, H is the operator. No, H is the Planck's constant. Okay, this is H cross. H cross is equal to H upon 2 pi, where H is the Planck's constant. Okay, I have not gone towards operators here, yet. We'll do the operator part a little later. What we are going to do is, we are just going to look at the systems first. Alright? Is this clear to all of you? So this is the free particle system. Free particle is a system where the potential is completely zero, and that means if the potential is zero, okay, for free particles we saw that the potential energy is zero, and if the potential energy is zero, it means that you will have a continuous energy spectrum. All possible energies are allowed for a particle. Okay, is this clear to all of you? Means of this that they behave like wave in free space. Yes, they behave like waves in free space. Wavelength is lambda is equal to 2 pi upon k, where k is the equation, k is the constant that you see, or the propagation constant that you see in the wave function. K is the propagation constant that you see in the wave function. Okay, is this clear? So these are free particles. This is a free particle system. Is this clear to all of you? Okay, so let's stop this particular class here, and we'll continue in tomorrow. We will continue tomorrow with the next topic, which is particle in a one-dimensional box. Okay, particle in a one-dimensional box where now potential is not zero everywhere. Okay, where potential is not zero everywhere. That's the reason light is wave during propagation. Yes, sort of you can say. Okay, that's a way in which we try to explain why light will show wave-like behavior. Okay, so now let me remind you, if all of you want to learn or prepare for CSIR NET, GATE or SET exams in exactly this way, we have launched an English version of our CSIR NET, GATE and SET courses. All the lectures will be conducted purely in English, and these courses, after the lectures, you will also get a recorded video. You will also get a daily practice problem. You will also get the PDF teacher handouts, teacher notes. You will also get a regular Sunday test series and previous year question discussions. All right. And all of this is at a flat 70% off. All of this you can get at a flat 70% off. Remember to use the promo code ITIHAS, ITIHAAS. Remember to use the promo code ITIHAS. Okay. फोटो में मैं दिख नहीं रहा हूँ. कौन से फोटो में? Oh, in this photo? Okay, yeah, that's me. That's me. Okay, I'm sure that you don't recognize me. I actually end up taking very bad photographs. Generally, that's what everyone tells me, and that's, of course, you can see here also. All right. Okay. So let's stop here, and we'll continue tomorrow with our next topic. We'll continue tomorrow with our next topic, and which is particle in a one-dimensional box. And that's a more interesting topic because that's the first or the simplest quantum mechanical system where we will see quantization of energy as well. Okay, so see you tomorrow. Until then, goodbye and happy learning. Good night, everyone.